B.4 General solution of fake coin problem. So in this video, we will solve the general version of the fake coin problem. So we need to consider all the possible n numbers greater than 2. Yeah. All right, so continue our discussion. Yeah. From simplest to general. When we consider the general case, we like to look at several different cases. First, n is multiple of 3. Because in this situation, we can make 3 piles completely balanced. Same number of coins each pile. Okay? Yeah. Perfect distribution. K1 pile, K2 pile, K3 pile. Okay? So that's simple. Then when we apply, weighings similar to our simplest case, right? Yeah. Coin 1, coin 2, here pile 1, pile 2. That's simple. 3 possible cases. Yeah. The middle one, pile 3 contains the fake. Case upper one, pile 1 contains the fake coin. Lower one, pile 2 contains the fake coin. See? After one weighing, we reduce the number of total coins from 3K to K. Okay? Problem size reduction. Problem size reduction. Here, we use that way. So the conclusion, size reduction from N to K. The next question, how to handle the case that n is not multiple of 3? Yeah, not multiple of 3. Yeah. We have 2 other cases not multiple of 3. 3k plus 1, 3k plus 2. So we need to consider both cases. Yeah. All right. The size reduction. Yeah. First, n equals 3k plus 1. When we make our distribution as balanced as possible, yeah. So how do we distribute 3k plus 1 coins? Pile 1 k coins, pile 2 also k coins, and pile 3 k plus 1 coins. So that's the best we can do. Okay? Best we can do. Now, when we do our first weighing, pile 1, pile 2, same number of coins, naturally, we put these 2 on the scale. Yeah. And 3 possibilities. Middle one, pile 3 contains the fake. Upper one, pile 1 contains the fake. Lower one, pile 2 contains the fake. Yeah. Now you can see what is the conclusion. So in our conclusion, yeah, size reduction. How do we describe the size reduction? Right? For this case, 3k plus 1 to k plus 1. This case, 3k plus 1 to k, and also k here. Yeah. So here, k plus 1. All right? Yeah. So you can see for the worst case, from n to k plus 1. That's the worst case, from n to k plus 1. Okay? Yeah. All right. When n equals 3k plus 2, can we do this in a similar way? Yes. but our distribution is like this. Pile 1 has k coins. The remaining 2 piles, each one k plus 1 coins. Yeah. But when we put on the balanced scale, we should put pile 2 and 3, and so on. Okay? Yeah. So the similar work like that. So I do not repeat here. So you can guess, you can imagine the result. The size reduction still from n to k plus 1. Still, right? So let us make our general case size reduction description. That's this one, from n to n over 3 ceiling function. Ceiling function. K plus 1 ceiling function. Okay, yeah. N over 3 ceiling function. So that's our formula description. So each weighing, we reduce the problem size 3 over n over 3 ceiling function. Okay, so that's from this analysis, our conclusion. Yeah. Next, now we want to solve the whole problem. Yeah. So we want to do the size reduction all the way to the last one, size becomes 1. Then we're done, right? So when we get to size 1 problem is solved. Yeah. So let's do that part. How to represent the minimum number of weighings in terms of n. How many rounds of weighing to find the fake? Yeah. All right. What is the simplest case? Yes. To find the answer, we want to look at the simplest case. Okay? Yeah. We use this way so many times. Yeah. So what is the simplest case? Look at the ceiling function. With respect to the ceiling function, what is the simplest case for n? It's pretty simple, where n is power of 3. Because in that case, the ceiling function is gone. We don't need to worry about the ceiling function. If we remove the ceiling function, we get the same number where n is power of 3. Yeah. So let us, list the problem size, number of weighing, and find the relationship between them. Before we make our first weighing, problem size 3 to the kth. Then after first weighing, problem size becomes 3 to the k minus 1, and so on. 2, 3 to the k minus 2, and so on. Okay? All right. The question, how do we keep track of the change in this way? How do we keep track of it? Right? We don't want to get lost. How do we keep track of it? Invariant. The invariant idea I used before. Here we use that idea another time. Find the invariant. What is the invariant from these two columns of the list? Yeah. So you can see the invariant E plus W. E, exponent. Yeah. E means exponent number. E plus W, W number here. Okay. E plus W equals K. K plus 0, K minus 1 plus 1, K minus 2 plus 2 equals K. That is the invariant. With this invariant, we can keep track of all the numbers. When we reach the bottom, 3 to the first E equals 1, so the W number should be K minus 1. Last one, when the problem size becomes 1, 3 to the 0 power, then number of weighing K. Yeah, so you can see the total number of weighings to reduce the problem size to 1 is K. Okay, yeah, so that's the answer. All right, yeah. So the K equals log base 3 of n. Log base 3 of n. Okay, yeah. All right. But in order to look at the general K, not necessarily power of 3, the general n, the weighing number should be an integer, right? Weighing number cannot be non-integer number. Yeah. So how to find the minimum number of weighings for the worst case? Integer number. Yeah. So we should modify this log base 3 of n to make it an integer. So there are two ways, floor function way and ceiling function way. Which one you feel a better choice? Better choice based on your intuition. Which one? Now, here you see the ceiling function, right? Here you see ceiling function. Should we also choose the ceiling function there? Yeah, because the ceiling function here give us some hint there, right? Hint. Yeah. Yes, the answer is this. Yeah. Why? Yeah, we can understand that easily. So why is that? Why is the ceiling function not the floor function? Yeah. It's pretty easy. Yeah. So let's look at our final solution. Yeah. For a general n, we can find k. Yeah. Whatever n is, we can always find an integer k such that 3 to the kth less than or equal to n, strictly less than 3 to the k plus 1. All right, so now let's do this kind of imagination. Yeah. All right. When you use this many coins containing one fake, lighter fake, you need k weighings, right? Yeah. Then when you have this many coins, then you need k plus 1 weighings. All right. Now you have n coins. That is the number between those two power of 3. Which one is the reasonable one? Yeah. You can think about if n is greater than 3 to the kth, that number, k weighings is not enough. Because more than that number. So k weighings is not enough. So you need k plus 1 weighings. Right? Rounded up. Rounded up. So that is the ceiling function. To do rounded up, you need to use the ceiling version. Yeah. So that is the final answer. Final answer. All right. So we solved the whole problem. Okay? Yeah. We solved the whole problem. Yeah. Try to understand the whole procedure. So not too complicated, but you need to apply many commonly used strategies and methods. All right, so let me stop here. Yeah.